Whenever I start learning a new subject or teaching a new subject, the first thing I like to talk about or to ask myself is, what is this stuff about? What questions is calculus trying to answer? What can you do with calculus once you've answered those questions? Well, with calculus, there's just one question. How fast is a function changing? That's it. I mean, it may sound simple, but even for relatively simple functions, it turns out to be non-trivial. But once we figure this out, we'll be able to answer other questions like what's the maximum value of a function, and what's the optimal value for a business process, and what's the average value of a function over a certain range. So if you've made it through a college or a high school algebra course, then you already know the answer to our question for one class of functions. When we're talking about a linear equation or a linear function, they all change at a constant rate, what we call the slope or the rate of change. So for this one specific category of functions, we've already answered our question. And on the slide here, I've got the formula that we use to calculate the slope or the rate of change of a line, and it's a very important one. To answer our question for other functions, we're going to use a common mathematical technique and take this formula that we already know, even though it only works in a very specific case, and expand on it to get a method that we can use to answer the question for a much larger group of functions. Now, take a look at this function. It's y equals x to the fourth power. And if I want to know how fast the function is changing between 2 points, okay, well, that's an easy question to answer. We just find what's called the average rate of change between the 2 points, which is same as the slope of the line through them. For example, if we wanted to find the average rate of change between x equals 1 and x equals 2, we would need to find the slope of the line through the points 1 comma 1 and up here 2 comma 16, which we can do using the slope formula. M equals 16 minus 1 divided by 2 minus 1, which is just 15. Well, okay, now suppose we did this again. This time using x equals 0 and x equals 1 instead. Okay, well now the points are 0 comma 0 and 1 comma 1, which makes the slope 1 minus 0 divided by 1 minus 0, which is just 1. Okay, well this is where the trouble starts. All right, we used the same x value, x equals 1, in both questions, and the two intervals, 0 to 1 and 1 to 2, were both the same length. But we ended up with dramatically different rates of change. So to get around this problem, what we'd really like to do is be able to talk about the rate of change for a single x value rather than a range, what's called the instantaneous rate of change. For example, we want to be able to talk about how fast the function is changing just at the point x equals 1, rather than between x equals 1 and some other point. Well, to talk about the rate of change at a point, we're going to play on this idea of the slope of a secant line. First, remember, a secant line is a line that crosses the curve at 2 points, like the ones we've been looking at so far. The analogous object that only crosses the graph at 1 point would be a tangent line, like the one I've drawn here. Now, obviously, the method we use for secants and the average rate of change isn't going to work in this situation. To find the slope of a line, we need 2 points. And I've narrowed the situation down to where we have just one. All right, so let's think back to our secant line. The slope of the secant line actually gives us an approximate value of the slope of the tangent line that we're looking for. Now, not a very good approximation in this case, right? But let's start from here and see if we can make it better. So suppose I use 1.5, comma 5.0625. That's 1.5 to the 4th power as the second point instead of 2 comma 8. Or excuse me, 2 comma 16. That secant line is visually closer to going in the same direction as our tangent line. So it should give us a better approximation of the slope. And if you do the calculations with the slope formula again, you'll get m equals 8.125. So, which does seem to be a little closer. Now, we can keep doing this, letting the secant lines get closer and closer to the tangent line by pushing the x-coordinates of the 2 points closer and closer together. But think about what that's going to do to the slope formula. As the x-coordinates of the points get closer together, the distance between them gets smaller. For example, 0.5 down to 0.1 and 0.01 and so forth. All right, now let's go back to the slope formula. Those values are going into the denominator of the equation. And as the denominator of an equation, the denominator of a fraction, gets bigger, as the denominator of a fraction gets smaller, the overall fraction gets bigger. For example, 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000, and so forth. Okay, so this should make you worried about our approximation method. As the x-coordinates of the points get closer together, the distance between them gets smaller, which means we could reasonably expect the fraction that we use to get the slope to start to blow up. That is, to get infinitely large, which isn't going to do us any good. You see, this is where Isaac Newton and Gottfried Leibniz, working independently, had a real genius moment back in the early 18th century. In the table on the left, I took 5 points, each one a little bit closer to x equals 1 than the last one. I started with x equals 1.5, then went to x equals 1.25, then x equals 1.1, and so forth. Then I calculated the slopes of the secant lines between the point we're interested in, 1, 1, and each of those points. Notice what's happening here. Not only are the slopes not blowing up and getting insanely big, they actually seem to be settling down and closing in on a single number, 4. Okay, this was Newton's and Leibniz's great breakthrough. They realized that because both the top and bottom of the fraction in the slope formula are getting closer to 0, the whole fraction has an unexpected behavior. Instead of either becoming 0 because the numerator is getting closer and closer to 0, or infinity because the denominator is getting closer and closer to 0, the fraction actually settles in on a single number that accurately reflects the slope of the tangent line. Now, everything I've talked about so far has been nice from a heuristic or a non-technical perspective. But there's a lot of talk about things like getting closer and closer or closes in on that weren't very precise and that definitely weren't mathematically precise. So the first third or so of a first semester calculus class is spent defining those concepts in a more precise mathematical language, and that's what we're going to do in the next series of lectures here. From there, we'll talk about formulas and methods that we can use to find this so-called instantaneous rate of change for specific functions. And then we'll see some of the practical things that you can do with those formulas and methods once we've derived them.